Good morning, everyone. Let's begin a new lesson. In this lesson, we will continue learn solving IP by branch and bound method. But in this lesson, we mainly studied solving MIP problem, that is, in section 6, a branch and bound algorithm for mixed IP. We should now consider the general MIP problem where some of the variables are restricted to integer values, but necessarily just 0 or 1 is generally integer values, but rest are ordinary continuous. For example, in this model, we noticed that these decision variables, j is from 1 to n, but the integer variables is from j to I. So in this model, some of variables is integer, but other is not real number. And this is the mixed IP problem. The key difference of the mixed branch and the bound method is the dividing branch. We have dividing for the two new subprograms according to reduction LP optimum solution if xj is not integer. We set xj less than bracket xj and xj greater than or equal to bracket j plus 1. Bracket j is the integer part of j. That, for example, if xj equal to 2.4, then bracket j is equal to 2. If xj is equal to 3.9, then xj bracket is the part integer is 3. So bracket j is the part of j. Respectively, each inequality becomes an additional constraint for that new subprogram. For example, if xj is 7/3, we set that xj is less than or equal to 3 and xj greater than or equal to 4, and add these two constraints to dividing branch. Now, steps for each iteration. The one step is branch. Among the integer restricted variables that have non-integer value in the optimal solution for the LP reduction of the subproblem, choose the first one in the natural ordering of the variables to the branch variable. That xj be this variable and xj its values in this solution. Branch from the node for the subproblem to create two new subproblems by adding respective constraints. Xj less than bracket xj and xj greater than or equal to bracket xj plus 1. Step 2. Bounding. For each new subproblem, obtain its bound for applying the simplex method to its LP reduction and using value of j for the resulting optimum solution. Step 3. Fastmin. For each new subproblem, apply the 3 Fastmin tests given below and discard those subproblems that are Fastmer by any of the tests. Test 1 is its bound less than or equal to j, where j is the current increment problem optimum solution. Test 2, the LP reduction has no feasible solution. Test 3, the optimum solution for its LP reduction has integer values for the integer rejected variables. Optimality test stop when there are no remaining subproblems, the current incumbent is optimal. Otherwise, perform another iteration. Now we see example 1. Solve the MIP by problem. Solve the MIP by branch and bundle method. And we noticed in this model, the decision variable x1, 2, 3 is all integer numbers. So this is the pure integer model. But x4 is not. But in this model, there is 4 decision variables. x4 is not integer. x4 is a continual real number. So this model is mixed IP program. Now we solved by branch and bundle procedure. Firstly, we delete all the integer restrictions and we get the LP relaxation. And we can solve these LP problems by simplex method and we get optimal solution. The optimal solution is x equal to 5/4. And we note that in this optimal solution, x1, 2, 3 is all not integer. So this optimal solution is not meet the requirement. So we need to dividing branch. And we set x1 is not integer and x1 is greater than 1 or less than 2. So we set x1 less than 1 and dividing B1 subproblem, we add another constraint is x1 less than or equal to 1. And we set x1 greater than or equal to 1. And we get another subproblems B2. B2 is added additional constraint. And these 2 problems is LP problem. We also solved by simplex method, and we find that B1 problem, the optimal solution is x equal to, and B2 subproblem is no feasible solution, so we can cut this branch. But in problem B1, we note that the optimal solution x2 and x3 is not integer 2, so it's not meet the requirement. We continue to branch. We notice that x2 is greater 1 and less than 2. So we set x2 less than or equal to 1, x2 greater than or equal to 2. To dividing 2 subproblems, and this is 2 LP problems or 2 relaxation LP problems, and we solved this by simplex method. We get to the optimal solution. We notice that and these 2 subproblems is not meet the requirements, so we continue to dividing branch. We continue to dividing branch. We note that in this optimal solution, x1 is greater 0 and less 1, and we set x1 equal to 0, x1 equal to 1. Why x1 is equal to 0 and equal to 1 other than greater than or less than? We find that we set x1 less than 0, but the negative constraint is x1 greater than 0. So both these inequality, we get x1 is 0. And this branch is x1 greater than 1. But this constraint is x1 less than 1. So we get x1 equal to 1. So this is the branch dividing. For these subprograms, we get the optimal solution. This is the optimal solution. And in these programs, no feasible solution. So we cut this branch. And in these subprograms, we notice that x1, x2, x3 is integer. So its solution is meeting our requirement, and the solution is finished. We notice that we cut this branch, and cut this branch, cut all the branch. So we finish the solution. And from the proceeding of this solution, we get the optimal solution is, this is the optimal solution. So in these programs, the optimal solution is x equal to 0, 0, 2, 1/2. And the objective value is j equal to 13, 1/2. And so we finish the solution of this problem. Now we introduce example 2. Solve the pure IP program by branch and bundle method. And the procedure is similar. We note in these programs, x1, 2 is all integer variables. So this program is a pure IP program. First, we solve the reduction LP programs. We delete all the integer restrictions. We get this LP program. We denote by LP0. And solve these LP programs, we get optimal solution is x1 equal to 2.5, x2 equal to 2.5, and the objective value is j equal to 87.5. And we notice that x1 and x2 are not integer 2. So this solution is not meet requirements. So we start dividing branch. We set x1 to dividing branch. We set x1 less than 2. Get this branch. This branch we denote by LPE, LP1. We need additional constraints x1 less than 2, and set x1 greater than or equal to 3. We get another subprograms LP2, and we notice in this model we need another constraint is x1 greater than or equal to 3, and this is LP model 2. So we simplex these two subprograms, we get optimal solution. LP1 is optimal solution x1 equal to x2 2.36, and this is not integer. And this problem, the optimal solution x1 is 3, and x2 is not integer 2. So we need to continue branch, and we notice that the objective value, this is great. So we choose LP1 to branch 2. So we choose this subprogram to branch. We set x2 less than or equal to 2, x2 greater than or equal to 3. We get two subprograms LP3 and LP4. And we solve these problems, get x1 and x2, and we notice the optimal solution is integer solution. So we can stop here. On the LP4, we also get the optimal solution is integer solution. So we stop here, true. And we notice that in LP2, the objective value is 8. 8 is greater than this integer solution objective value. So we need to branch 2. We set x2 is less than 1, x2 is greater than 1. We get 2 subprograms, LP5 and LP6. And LP6 is no feasible solution, so we cut this branch. On LP5, we get the objective values is 17.2.5 and is less than these bounding values. So we cut this branch 2. On LP3 and LP4 is stop and is cut branch 2. So we finish the procedure of this example. And from this procedure, we get the optimal solution is LP4. And x1 is equal 1, x2 is 3, and J is 75 is the orange IP program's optimal solution. Now we introduce example 3, solving the mixed IP by branch and bound method. This model, we notice in this model, there are 3 decision variables. x1, x3 need integer numbers, and x2 is not integer numbers. So this is mixed IP programs. Similar to the former 2 models, we solve the reduction program. We denote program B. It is deleting the all integer rejections. So it is the LP program. We solve this program, get an optimal solution. And we notice that in this solution, x1 is not integer. So this solution is not meet requirements. No, so we continue branch. We choose x1 to branch. We set x1 less than 5 and x1 greater than 6. We get 2 reduction subprograms, B1 and B2, and B1 and B2. And we solve the B1 programs. We get the optimal solution x1 equal to 5, x2 20 sevenths, x3, and the maximum J is 194 sevenths. And in this optimal solution, we notice that x3 is not integer 2. So this optimal solution is not the solution we needed. So we continue branch. We choose B1 to branch. We set x3 less than 3, x3 greater than or equal to 4. We get these 2 subprograms, B11 and B12. We solve these 2 programs by simplex method, and we get this optimal solution. X1 and x3 is integer, so the solution is meet our requirements. And B12 is not feasible, so we cut this branch. And we bound the J is 1074. And these programs is the optimal solution meet our requirements. So we write the graphic procedure of this program as this graphic. We note that first to show LPB and the branch PBE B1, B2, B1, B2 on the branch 2, B11, B12, and this 2 subprogram is not feasible. So we cut on the list, we get the optimal solution. So this is the optimal solution of the orange problem. So that's okay. Solve these problems. That's okay. In this lesson, we have studied the branch and the bound method by solving mixed programs. And in these lessons, we noticed that to solve mixed programs is differs from BIP. BIP problem is the branch steps. That's okay. Thank you very much.